So, hello. Okay. Coding. Okay. Okay. So, hello everyone. Thank you to the organizer of the conference for giving me the possibility to talk. So, I'm a French master student in Marseille, and I've been in Ottawa for 6 months, where I work with Rick Bluth and Phil Scott, and I will continue in PhD probably here. And so I'm going to talk about symmetric powers and symmetric modal gate theories. And I will explain conjectures, because for the moment it's still conjectures, for characterizing the symmetric powers in different ways than the usual definition. And one characterization will be related to the differentiation of homogeneous polynomials, and one other, it will be in terms of a special kind of bialgebra. So in the first part, I will give some background to be able to state the conjectures. After that, I will state these conjectures. And in the last part, I will explain why I'm convinced that they are true and what are the idea of the proof I'm trying to do. So we are going to work in a symmetric monoidal coupleless linear categories. So it means that it's a symmetric monodal category enriched over Q plus modules. So Q plus is not a ring, it's a semi-ring, so like a ring but without the negatives, and we can look at modules over a semi-ring. And so every set must be a Q plus modules, and we want that the tensor product and the composition are bilinear with respect to the addition and the multiplication by scalars by positive rational scalars. So it's what we call a symmetric monodal Q plus linear category. So some example. So the category of modules where R is a commutative Q plus algebra. So a Q plus algebra, it means that we have a semi-ring homomorphism from Q plus to R. A sub-example is the category of vector spaces on a field of characteristic 0. Another sub-example of this first example is where R is a commutative idempotent semi-ring. So idempotent means that x plus x is equal to x in the semi-ring. And for instance, if we take a Boolean algebra, x plus x is x or x and equal to x. So the modules over a Boolean algebra, it's an example of symmetric monodal Q plus linear categories. And also the category of set and relations, which is pretty original, because the category of set of relations, if we look at the relations from A to B, it's a modules over the Boolean algebra with exactly two elements, true and false. And so it gives a symmetric monodal Q plus linear category. So after that, we need to know what are the symmetric powers. So in a symmetric monodal category in general, you can define the n symmetric power of an object by this equalizer. So in the left of the diagram, you have factorial n permutations. In the symmetric monodal category, you can define a natural transformation, an exchange for every permutations. So you have all these exchange on the left, and you look at the co-equalizer, and it gives you the n symmetric power. So the symmetric power can be interpreted as space of homogeneous polynomials. Yes, and in a simple example, if we take a vector space on a field, if a basis of A is x1 and xq, when we take the n symmetric power of A, it gives exactly the homogeneous polynomials of degree in x1 and xq. And so homogeneous of degree n, it means that all the terms of the polynomial are of degree n. So we will really use this interpretation of symmetric powers as space of homogeneous polynomials to give a different characterization. In the Q plus linear categories, when we are able to multiply the morphism by positive rational scalars, we can express also the symmetric powers by the same diagram, but this time in the equalizer version. And in general, in a symmetric model gate array, what we obtain, this Sn of A in general, it's not the n symmetric power, but what we name the divided power. But when we have the rational scalars, positive scalars, and for instance, in a space of in a vector spaces of characteristic 0, the notion of symmetric powers and divided power are equivalent. And it's why in this case, we can consider the n symmetric power either as a quotient or as a subspace of the nth symmetric power. And we are going to use this equivalence because this equivalence in this situation gives a third definition, the n symmetric power. You can express it at the split. Yes, when the sum of permutation divided by factorial n is a split idempotent, so the object in the middle is the n symmetric power. And so to express this definition, you need the ability to divide by factorial n. And so we are really going to use this definition of symmetric powers in the symmetric model K plus linear category. So one of the characterizations, it will be in terms of graded co-differential categories. So the notion of differential categories and a co-differential category, it's a category such as C-op is a differential category. The notion of differential categories was defined like 15 years ago by Richard Bluth, Robin Coquette, and Robert C. And the idea is that it's a categorical setting for doing differentiation. And so I've defined the graded version. And so what you have, in order to have a graded co-differential category, you need to have a symmetric monoidal category. And you have a family of endofunctors that I write Sn. So it's not necessarily the symmetric power at the beginning. And so Sn of A, it's going to be a space of differentiable functions which of some grade n. So for instance, it can mean that Sn of A can be the space of homogeneous polynomials of degree n, or it can be also the space of polynomials of degree less than n, or maybe it could be also a space of functions which are n times differentiable. And so we want that this Sn gives a graded monad. So graded monad, it's like a monad, but with grades. So it means that we are able to compose, we have a map from a natural transformation from Sn of Sp to Snp. So it means that we can compose these functions. And when you compose, you multiply the degrees. When you compose, in the example of homogeneous polynomials, when you compose, you multiply the degrees. You can inject the variable as function of grade 1. And so for the homogeneous polynomials, the variables in the space give you a particular simple homogeneous polynomial of degree 1. For the example of function differentiable in SEM, it's different because you have to consider an addition which is equal to max, and so. But really, what interests us is when Sn is the n-symmetric power. So also you have the ability to multiply these functions. So when you multiply an homogeneous polynomial of degree n by one of degree p, you sum the degree. And the most important, you have a natural transformation which is meant to differentiate. And so we want that these deriving transformation verify 4 properties which express the Leibniz rule, the chain rule, and 2 other facts related to differentiation. And so all these, so there is a list of axioms like this, which gives what is a co-differential category, graded co-differential category. So every symmetric monoidal K plus linear category with Sn of A defined as the n-symmetric power gives a graded co-differential category. And how do we define this deriving transformation? For instance, if we look at the category of vector spaces and the field of characteristic 0, we have this map. We have this map D3. What is going on? Oh, sorry. Sorry, I have an issue. Sorry, I must just plug my computer.
Okay. We cannot hear you now.
I guess so.
No, it's fine.
It's fine. Okay, so sorry for this interruption. Sorry. Yeah, so we have this D3 from the third symmetric pair to the second symmetric pair of A tensor A. So we can take if we look at the vector spaces A of base, this X and Y, in the third symmetric pair, you have this polynomial. And when you differentiate what you do, or it is defined, you take the sum of the partial derivatives, tensor, the variable with respect to you differentiate. So it works like this. So x squared, it's the partial derivative with respect to y, and 2xy is the partial derivative with respect to x. So like this, you define a graded codifferential criterion. What a special property which is verified in the case of homogeneous polynomials is the Euler identity. So the Euler identity tells you that. So if you have a ring or commutative ring or commutative summary, you can look at the polynomials with the scalars in this ring and with variable x1 and xq. And you know that P is homogeneous of degree n if and only if you have this equality. And we can express this equality with the language of graded codifferential characteristic, because you see here, I told you like the differential, it's the sum of partial derivative, tensor, the variable with respect to your differentiate, and you see that you have almost this in the Euler identity, but without the tensor. So we can express what is this Euler identity in a graded codifferential characteristic, and so we can express this like this. So we differentiate, it gives this sum with the tensors. After that, we just use the unit of the monad. It's not, in the case of the symmetric power, you do nothing. And after that, you multiply, it gives you this sum, and you want that it's equal to the degree of the homogeneous polynomials times the identity. So a conjecture, if we have a graded codifferential characteristic, so we have this natural transformation with all the axioms in the definition of graded codifferential characteristic. If we add this axiom also, the Euler identity, we must obtain necessarily for Sn of A the n-symmetric pair of A. A second conjectural characterization is in terms of bialgebra. So what I call a special graded bialgebra, it's you have in a symmetric modal characteristic, you have a family of objects indexed by the natural numbers. The first one is the unit of the symmetric modal characteristic. You have a family of multiplication. When you multiply, you sum the degree. You have a family of co-multiplication. So concretely, in the example of homogeneous polynomials, if you take an homogeneous polynomial of degree n plus p, when you co-multiply, you divide it in a part of degree n, tensor a part of degree p, and you sum all the possibility, and it's going to give you this structure. So the axiom, we say that we want that when p equals 0, this multiplication and co-multiplication are the identity. If we have a symmetric strict monadal characteristic, if it's not strict, you can say that we want that it's natural isomorphism. And we want the multiplication and co-multiplication to be commutative and co-commutative, associative and co-associative. And the most important are these two diagrams. So the first one is similar to the diagram for bialgebra, but graded, so we have to make a sum. And the second one is more new. So it's like maybe there is something like this for a special Frobenius algebra, but not for algebra. And now the difference is that we have this coefficient. So this first diagram is really related to really express an higher order Leibniz rule of differentiation of polynomials if you really look at what it does. And the specialty, when p equal 1, it's the Euler identity, and when p is different to 1, it's the generalized version. So we know that in a symmetric model K plus K theory, if an is the n symmetric power of A1, we obtain a spatial graded bialgebra, and the conjecture is that the reverse is true also. If you have a spatial graded bialgebra, n is going to be the n symmetric power of A1. And also, a conjecture is that these the commutativity, co-commutativity, associativity, and co-associativity are redundant in this definition. So now I'm going to explain why I think these conjectures are true. So now it's going to be a little different. I will look not at just the symmetric power of one object, but I will look at symmetric model K plus linear categories, where we have all the symmetric powers. So in this case, when we have all the symmetric powers, we want the symmetric powers to be an endofunctor, to be endofunctors. And we want in the definition of symmetric powers, like on this slide, that Rn and Sn are natural transformations. And in the different characterization, we will want also that all the morphisms are natural transformations. So in fact, more precisely, these conjectures are that when you have, suppose that you have a family of endofunctors Sn, such that the first one is the unit of the symmetric modal category and the second one is the identity. So I conjecture that we have bijection between different family of natural transformations, which gives the different characterizations. So in this definition, we require two natural transformations Rn and Sn, but we can build other type of natural transformation using them. For instance, you can build this type of multiplication and commultiplication by using in the most simple way the Rn and Sn. So I conjecture that there is a bijection between this first family of natural transformation and this second with multiplication and commultiplication, such that when p equals 0, we obtain the identity, and we have these two equations verified. So I suppose that it's equivalent to add to this four axiom, the associativity, co-associativity, commutativity, co-commutativity, as I said before. I suppose also that we have another characterization in terms of what is known in physics as annihilation and creation, annihilation and creation bosonic operators. So the n symmetric power, it can be interpreted as the space of states of n indiscernible bosons. And so the creation, it means that you have the state of n indiscernible boson. You add one boson, and you obtain the state of n plus one indiscernible bosons. And also you can take one boson in this state and extract it. And it gives you the annihilation natural transformation. So I suppose that if we have two natural transformations like this, which verify these equations, it gives you also necessarily the symmetric powers. And also, if we have all the bunch of equations for defining graded codifferential character n, which verifies the Euler identity, it must give you also the n symmetric power. So in these conjectures, it's so you see really the thing is that when you have one of these kind of natural transformation, you have really a trivial way to define another set of natural transformation. Like you combine them in the most natural way. And the most difficult part is to go from the creation annihilation operators to these two natural transformations, which are in the basic definition of symmetric power. And more precisely, the most difficult part is, so it's easy to go from this second equation, the specialty, to this equation Sn next Rn equal 1. What is difficult is to get Rn Sn equal to the sum of permutation from this first equation. So more precisely, really the crux is if you have a family of natural transformation like this, we verify these two equations. So these, So these big equations, when you put n equals 0, it gives you this thanks to C0 equivalent identity and S0 equivalent identity. So what is difficult is you start with this, you combine this creation, by combining these creation operators, you can obtain a map from A tensor n to Sn of A. By combining these annihilation operators, you can obtain a map from Sn of A to A tensor N, and you want that it gives you the sum of all the permutations. And so to reobtain N and Sn, you just have to add a factorial. But really what is difficult, so to prove from these equations, prove this equation. So on the next slide, or on the last slide of my presentation, I'm going to present the big drawings which prove this equality, which proves that if we have this equality for n equal 1, n equal 2, n equal 3, and n equals 4, n equal 4, you obtain this equality also for n equal 1, n equal 2, n equal 3, and n equal 4. In the case n equal 1 and n equal 2, there is really nothing. The case n equal 3, you have to do something, and I'm going to present the most difficult case, n equal 4. So to prove the conjecture, I must prove this thing for all integers. So how does it work? So I must prove that this thing is equal to this sum of permutation. I'm going to do something slightly different. I'm going to talk about rewriting. So it's the same to prove this equality for n equal 4, or to prove that if I start with this graph and I use these two rewriting rules, there is only one and only one path to arrive to any permutations of the symmetric group of order 4. And so proving this proves the precedent equality, it's equivalent. So there is really an interpretation. Each of these graphs represents a set of permutations. So these ones are the set of one permutation of order 4. The first one is a set of 4 permutations, is a set of all the permutations, the 24 permutation of order 4. You see that in this graph, all the entries are related to all the outputs. So you can draw any permutation in this graph. You can go for any of these permutation, you can realize it in this graph because all the entries and outputs are realized. When I rewrite the central part by using this, I'm going to restrict myself to a more little set of permutation. In this graph, now, the first entry is related only to the 1, to the 2, and to the 3 output, the third output. So it means that this graph represents the set of permutation of order 4, such as sigma of 4 is different from 4. And after that, I specialize again. This graph represents only 2 permutation. And so we see that to obtain any graph, you have to choose the good rating in each step, and there is only one and only one path to obtain any permutations. And so if I prove that this fact about the rating for all the graph, for this graph, for n equal 4, n equal 5, for all integers, it's going to prove the conjecture, the most difficult part, and most of the, and I will be sure that most of these conjectures are true. And so I really understand how to make the proof. The difficulty is that I struggle to formalize this kind of graphs and to explain really by a theorem what I see concretely in these pictures. So it's really a problem about formalization, because it's like with proof nets in linear logic, it's difficult to formalize them and to work rigorously with them. So it's the end of my talk. Thank you for your attention.